Hello. Okay, so the purpose of this video is to basically give you more information on logarithms. Okay, so let's start off with this first example here. We want to prove that the inverse of this function f of x equals 2 raised to the power of x is this function here, log base 2 of x. Okay, and we're going to do that by using this idea of inverses that I showed you guys in the past. Okay, so the first step, what we're going to do is we're going to substitute y for f of x here. So there's step 1 here. So this is y equals 2 raised to x. Okay. Step 2. Now what we're going to do is we're going to swap the x's and the y's. So we're going to swap the x's and the y's here. Okay. So by swapping the x's and the y's, this is x equals 2 raised to the y. Okay. Third step, what we want to do is we want to solve for y. Okay, so if we were to solve for y here, what I see is we can take the common logarithm of both sides. So log of x equals log 2 raised to the y. And then what we can do is, you see this exponent here, we can, anytime we have an exponent for logarithm, we can drop it in the front. So this is log x equals y times log 2. Okay, so now what we want to do in order to get y by itself, so to get y by itself here, we can divide by log of 2. Okay, so we're going to divide by log of 2. So what we're left with is y equals, so log of x divided by log of 2. Okay, now if we were to reverse the change of base formula, so reverse the change of base formula, this is the same thing as log base 2 of x. Okay. Now what we've done is we've solved for y. Now that we've solved for y, we can write out our fourth step. So we're going to replace y with the inverse of f of x. So inverse of f of x equals log base 2 of x. Log base 2 of x. So just like that. Okay, so that's what I'm asking you to do. Okay, similarly, what some of you guys like to do is, I know some of you guys like a, right? So do it from here. This is 2 raised to the y equals x. This is our exponent. This is our base, and this is our answer. And we can spell b with the logarithm. So b is 2, x is our answer, and our exponent is y. And as you can see, that's exactly what we have here. We just have to replace this with the inverse of f of x, and that would be our answer. Okay, so however you want to do that, that's entirely up to you. Okay. Okay. So I'm going to scroll down, and I'm going to show you more examples. Okay. So here, so using the logarithm rules shown in previous lessons, we want to condense this into a single logarithm. Okay, so generally what we have here, anytime we have a coefficient in front, what we're going to do is we're going to bring it up front. I'll put that in different colors so you guys can see that. Okay, so anytime, yeah, so this we're going to put up front. So anytime we have a coefficient, we're going to put up front. This is log base 4 of 8 cubed minus log base 4 of 2 raised to the 5th. Okay. So if we were to go ahead and simplify what we have on the insides here, so basically we could do 8 cubed. So if we do 8 raised to the 3rd power, that looks like it's going to be 512. So what we have here, so this is log base 4 of 512. And this is log base 4, 2 raised to the 5th is 32. Okay, so now what we can do is we can go ahead and simplify this. So we're going to use the division because we have a subtraction sign here. So log base 4 of 512 divided by 32. So log base 4 of 512 divided by 32. So if I use a calculator and did 512, so right here, so we did 512 divided by 32, we get 16. So this is log base 4 of 16. If you were to evaluate this, this happens to be 2. This answer is 2, but I'm just asking you to condense this into a single logarithm, and that's fine. Okay, For this next example here, what we're going to do is we're going to do a combination of division and multiplication. So this expression is log base 4 of 8 divided by 4 multiplied by 6. Okay. So 8 divided by 4 is 2. 2 times 6. So this is log base 4 of 12. Log base 4 of 12. Okay. This one here, I see we can simplify the inside here. So this is the same thing as 2 times log base 6 of 45 divided by 5. And then we're going to add log base 6 of 3. Okay, so as you can see here, we can actually simplify the inside here. So this is 45 divided by 5. So this is 2 times log base 6 of 9 plus log base 6 of 3. Okay, now what we're going to do is we're going to go ahead and bring this coefficient on top. So log base 6 of 9 squared plus log base 6 of 3. 9 squared is 81, log base 6 of 81 plus log base 6 of 3. Okay. So running out of room, if we go ahead and simplify this, as you can see here, so the addition sign implies multiplication. So this is log base 6, 81 times 3 is 243. 243. And there we go. So that's how you would answer this one. Okay, let's go ahead and look at these particular examples here. So same idea, we have a 7 in front, we're going to bring it up. We have a 4 in front here, we're going to bring that up. Okay, so this is log base 5 of x raised to the 7th plus log base 5 of x squared raised to the 4th. Okay, recall. So now what we want to do is we need to simplify the inside here. This is x squared times x squared times x squared times x squared. If you do that out, that should be x raised to the 8th. Or in other words, 2 times 4 here, you'd multiply those exponents together. Log base 5 of x raised to the 7th plus log base 5 of x raised to the 8th. Now what we can do here is, as you can see, we have an addition sign here. So that says we're going to multiply this and this. Okay, so what we have is log base 5 of x raised to the 7th times x raised to the 8th, and x raised to the 7th times x raised to the 8th. If we simplify that, we add the exponents together, and we have log base 5 of x raised to 15. Okay, so that's what that's equal to. Alright, so let's go ahead and look at this particular example here. Okay, so as you can see, we have addition and then subtraction. So basically what we have here, we're going to go ahead and write. So since we have addition, so we're going to multiply the insides and the 5, and we have subtraction here, so we're going to divide. Okay, so this is log base x, and then 7 times 10 is 70 divided by 5. So 70 divided by 5 is going to be 14. 70 divided by 5 is 14. And that's how that one works. Okay. This one here. So as you can see here in the parentheses, we can simplify that. So this is 2 times log base 9. So 2 times 4 because we have the addition here. So this is log base 9 of 8 minus log base 9 of 8. Okay. So generally what we can do, actually, hold on. Let me go ahead and put this on a different line so it doesn't look confusing with that. Okay, so what we have is 2, and we said log base 9 8 minus log base 9 of 8. Okay. So if you actually see, you could combine like terms. You see like this and this here. This is just basically if these were variables, if this was x, this is just 2x minus x. And that would be just, you'd be just left with log base 9 of x. That's one way you can do it. But let's actually solve this. Let's prove that we can do this using those properties that I showed you earlier. So this 2, we're going to bring it up, and we're gonna write it as log base 9 of 8 squared minus log base 9 of 8. Okay. 8 squared is going to be 64. So log base 9 of 64 minus log base 9 of 8. Okay. So now what we want to do is, if we want to go ahead and simplify this, so as you can see here, this minus sign, so this says we have log base 9 of 64 divided by 8. We're going to divide. And that says we are left with log base 9 of 8. Oh, shoot, maybe I should make that a little bit. Let's see, hold on. There we go. You guys can kind of see that. So log base 9 of 8. Okay. So that's basically how we do that one. And similarly, like I showed you guys here, you could also combine like terms. If you saw, you could combine like terms, and that's log base 9 of 8. Okay, so that's the first page. Okay, please let me know if you have any questions on it. Okay, bye. Hello. All right, so now to go over the second page. All right, so what I want to show you here is any logarithms without a base, as you can see in the bottom here, are assumed to have a base of 10. Okay, so some of you might be wondering, like, well, how are these examples even calculated? So let's just take this first example. Let's say we wanted to find log of 6, right? So as you can see there, like, how is it even getting this number in the first place? Okay, so basically what I want to try to get across here is any logarithms without a base here are assumed to have a base of 10. So that's a common logarithm. So if I type in log base 10 of 6, well, this is the same thing as what we have up here, as you can see. Okay. Basically what I'm trying to get at, right? So if I were to actually convert this, you know, like if I have log 6 divided by log 10, these expressions are all the same thing, okay? In other words, what we have for this, so basically, this is the exponent of the base of 10. So for example, if I have 10 and we have this exponent here, we raise it to 0.778, 0.778. We can even keep more decimal places, 1.5 here, as you can see here. This would be our answer. You know, this is base, answer, exponent. So base, and then the exponent, and this is our answer. Okay, so again, anytime you don't see a number underneath, you assume it's a base of 10. Okay, so basically what I showed you here is that all of these examples are all represented by the same thing. You can test this out with other examples here, but I just wanted to show you that just for your curiosity. Okay, so I'm going to go down. Okay, so on the bottom here, so any logarithms with a base of e are called natural logarithms. Okay, recall we have Euler's number, so e is approximately 2.718. Okay, so natural logarithms can be written as shown here. So as you can see, if you have a base of e, the shorthand for this is ln of x. So that's called a natural logarithm. Natural logarithm, n here standing for natural, and L for logarithm. So this is basically a shorthand that mathematicians use rather than writing log base e. Okay, so on the left hand side here, as shown here, this is pronounced as log base e of x. The right hand side over here is pronounced as the natural logarithm of x. Okay, so I'm just showing you some examples here. So just some examples. You can this is the same thing as ln of 5. This is the same thing as ln of 10, and so forth. Okay. So what we have here is we want to rewrite the following expressions as natural logarithms. Okay. So what we have here, so if we wanted to express this as a natural logarithm, so what we have here, this is the same thing as ln of x. Okay. This one here is the same thing as ln of 9. This is the same thing as ln of x cubed. And then this is the same thing as ln of 15. So all we're doing is anytime you see this log base e here, basically what a mathematician will do is they'll just abbreviate that and put ln in front. Okay, so that's generally how that works. Please let me know if you have any questions. Okay, bye. All right, so let's consider another way we can solve for x. But instead of using common logarithms like I showed you earlier, let's go ahead and use natural logarithms. So again, common logarithms have a base of 10, natural logarithms have a base of e. Okay, so for this particular example here, we have 2 raised to the x equals 9. Okay, so let's start off by writing both sides with a natural logarithm. So let's say we have this here. What we can do is, so in the past, what we've done is usually we have log of 2 raised to x equals log of 9. So like I told you is usually, well, in the case where you don't see a number underneath, we assume it's a 10. But in this particular example, rather than putting a 10, we're going to put an e. Okay, so basically what we, so I'm just going to show here. So what we did here is we rewrote both sides with the log base of e. Okay, now what we can do is we can drop this exponent in the front. So we're going to drop that exponent in the front. So by doing so, this is the power rule. Right, so we use the power rule in order to bring that the exponent in the front. Okay, like I showed you in the previous examples here, anytime we have this log base e, all of this stuff, this is the same thing as just writing the shorthand ln. Okay, so this here, basically, as you can see, when we go from here to here, all we're doing is we're just writing it with the ln or natural logarithm notation. Now what we want to do is we want to get x by itself. So to get x by itself, we can isolate what we have here. So we can divide by ln of 2. Right? So if we go ahead and cancel that, what we're left with is x equals, so ln of 9 divided by ln of 2. Now, if we were to actually go and simplify that, so ln of 9 and then divide by ln of 2. So I literally just am typing in ln into decimals. For my keyboard, and you get about 3.17, okay? 3.170 if you were to approximate that. And basically, what you're going to realize is you get the same thing if you actually were to use logarithms as well. So let me just go ahead and show that to you guys. So if I put log 9 divided by log 2, it just so happens these are just going to be the same thing. Now the reason why that happens is because the change of base formula, no matter if the numbers are the same here, you're going to get the same result. So even if I put log base e of 9, and then I divide that by log base e of 2 here, so this is the same thing as ln. So that's why it comes out the same. I could even change it to any number if I wanted to. I wouldn't recommend doing this, but I could literally change it to any number that I want, and basically you're going to get the same thing. But long story short, basically whether you use, if you have log here, if you don't see a number, you assume it's a base of 10. If you see ln, you assume that the base is e. Okay? So what I'm providing you here is a completely alternate method if you decide to do this way. Okay. Now, what mathematicians like to do is rather than writing log base e every single time, because that can get kind of redundant, it's easier just to write ln, which stands for natural logarithm. Okay, so let's take this particular example. So 5 raised to the x equals 76. So generally what we can do is, for this particular problem, what we can do is we can rewrite both sides with a natural logarithm. So ln of 5 raised to x equals ln of 76. Okay? So now what we want to do is we're going to go ahead and take this exponent here and we're going to drop it in the front. So x times ln of 5 equals ln of 76. Okay? Now what I want to do is we want to get x by itself. So to get x by itself, we're going to divide by ln of 5. Okay? So this cancels, and we're left with x equals ln of 76 divided by ln of 5. Okay? So let's go ahead and calculate that. ln of 76 divided by ln of 5. So this is 2.691. So this is approximately 2.691 based on what we have here. Okay. Now similarly, if you guys did bay, right? If you guys did bay, this is log base 5 of 76 equals x. So this is log 76 divided by log 5. And what you're going to get is whether, if I type that in, you're going to get the same thing as well. Log 76 divided by log 5. So again, what I'm providing you is a completely alternate method. So again, like I showed you guys earlier, if you don't see a number here, what you're doing is you're assuming the logarithm has a base of 10, the common logarithm. And then up here, if you're using the ln notation, you're assuming the base is e. Okay, but that's how you would do that one. So let's go ahead and look at this one. So 9 raised to the x equals 2 over 5. So let's solve this by using natural logarithms. So we have ln of 9 raised to the x equals ln of 2/5. Okay, so like I showed you guys here with the power rule, what we're going to do is we're going to drop this exponent down. X times ln of 9 equals ln of 2/5. Okay, now what we're going to do is we're going to go ahead and take this x, so we're going to divide by ln 9. So divide by ln 9, this cancels, and we're going to go ahead and simplify that. So we have ln of 2/5 divided by ln of 9. Okay, and then we will see what that's approximately equal to. So ln of 2/5 and divide by ln of 9. So that's approximately negative 0.417. Negative 0.417. And there we go. So that's how you would calculate that using natural logarithms. And again, if you guys just prefer using just common logarithms, that's fine. You can do it that way too. It's all a matter of preference. Whatever you decide is more comfortable with you, just stick with that method. Okay? So this here, if we change a base, this is just log of 2/5 divided by log 9. And basically what's going to happen is you're going to get the same result if we calculate it that way as well. So if I did log 2 over 5 and divide by log 9, as you can see, we're going to get the same result. Okay, and the reason why is because, well, we're changing the bases and it's consistent. Okay, so that's how you would do that one. Okay. Now what I'm going to do is I'm going to show you an optional method here, okay, to solve these word problems. So again, up to you if you want to solve it using natural logarithms. If you guys prefer just Bay or a common logarithm method, that's fine. Just stick with that. Okay, so pretty soon I'm going to go ahead and show you how to do it using natural logarithms. Okay, bye. All right, so let's do this. Okay, so this is the same word problem that I've shown you now for the third time. Okay, so now what we're going to do, I'm just going to go ahead and tell you these are the values and stuff. This is the exponential growth equation, and we just plug it in. Okay, so now what we want to do, if we want to isolate this expression, 1.5 raised to the power of t, we're going to divide both sides by 0.59. Okay, so basically what we can do is if we divide both sides by 0.59, so let's go ahead and do that. So we have 6 divided by 0.59. So this here, so this is going to be 10.1695 equals, so if I cancel it out, this is 1.5 raised to the power of t. Okay, so I totally see you guys. If you guys like doing Bay, I can see you guys already doing log base 1.5 of 10.1695 equals t. That's fine, you can go ahead and solve it. Now, let's go ahead and solve this using natural logarithms instead. If we use natural logarithms, so we have ln of 10.1695 equals ln of 1.5 raised to the power of t. Okay, similar idea as you can see here. So with this exponent, we're going to drop it in front. So this is ln of 10.1695 equals t times ln of 1.5. Okay, now what we're going to do with this is we're going to go ahead, so you see this t here, we're going to divide by ln of 1.5. So divide by ln of 1.5. So this cancels, and we can get t by itself. So we can go ahead and calculate this. Okay, so let's go ahead and do that. So we have ln of 10 0.1695, and we divide that by ln of 1.5. So by calculating this here, so this is going to be about 5.720 days. 5.720 days. 5.720 days if we were to round to the nearest thousand. Okay. Now again, what you could do instead, so as you can see here, like if you guys use the common logarithm method, if you guys prefer that, that's fine. Just do it that way. So you know, like if you have log what is it, log base 1.5 of 10.1695, yeah, you can do that. Or even like this, log 10.1695 divided by log 1.5, that's fine. So all these expressions will come out the same no matter which way you decide to go ahead and evaluate it. Okay, so that's it for that problem. There's one last problem that I want to show you, and now it's the third time again that I'm showing you this particular problem. So basically, yeah, just gonna run through it. You're gonna use exponential decay, and then basically you're gonna end up with this here. Okay, so what we want to do is this number on the outside, we're going to divide. We're going to divide by 28,000. Divide by 28,000. So this cancels, and we go ahead and simplify. So 5,000 divided by 28,000. So 5,000 divided by 28,000. So it's 0.17857. 0.17857 equals 0.905 raised to the power of t. Okay, so from here, if you guys liked the common logarithm method, stick with that. Just do log 0.905 of 0.17857 equals t. That's fine, and then you can go ahead and solve for t. Or if you guys prefer the the natural logarithm method, we have ln of 0.17857 equals ln of 0.905 raised to the power of t. Okay, so what we're going to do, we're going to go ahead and take this t, and we're going to place it right in the front. So this is ln of 0.17857 equals t times ln of 0.905. So what we have here, what we can do in order to solve for t, so in order to solve for t here, what we can do is we can divide by ln of 0.905. So divide by ln of 0.905. That cancels, and we're left with t is going to be approximately. So let's go ahead and see what that's approximately equal to. So we have ln of 0.17857 and divide by ln of 0.905. Okay, so we get 17.259 if we round to the nearest thousand. So 17.259 in this case, and that's how many years it would take for the value of the truck to be worth $5,000. Okay. Similarly, as I showed you here, so what we have is this is the same thing as log of 0.17857 divided by log of 0.905. So if you were to actually go ahead and do that, so if you did that instead, log 0.17857 divided by log 0.905, you're going to get the same result. Again, the only difference between these is if you're using a common logarithm, you're assuming the base is 10. If you're using a natural logarithm, you're assuming the base is e. Okay? Even if you were to type it in that format, so like log and then 0.905 and then 0.17857, 0.17857, as you can see here. So these would represent the same thing. So up to you how you decide to go ahead and evaluate that. Okay, so that's basically it. That's basically what I wanted to show you for that. Okay. So that's just kind of checks to see that works. Okay, there's one last thing that I want to show you, and I just remembered this earlier. So earlier when I showed you this inverse example, I forgot to show you the purpose why I wanted to go over that particular example. So I'm going to use this now to go time now to go over the purpose of this, right? So let's go ahead and graph this function, y equals 2 raised to the power of x. So y equals 2 raised to the power of x. Remember, when we find the inverse, basically what we're doing is we're going to create a reflection. Okay, so we're going to create a reflection across this line y equals x. Okay, and then what we have here is that if we found the inverse, we said the inverse, as you can see here, this was y equals and log base 2 of x. So wow, if you look at that, isn't that so cool? What we have here is that when we create the inverse, we create a reflection across this line y equals x. And that's why I wanted to show you that. It's pretty cool. Okay. And yeah, that's it. Okay. And with that being said, that is it. Okay. So congratulations. This was the last lesson, or this is the last lesson of my Algebra 2 class this school year. So congratulations for making it this far. Thank you for listening to my videos, if you are watching them, if you have ever watched them. And I wish you the best of luck next year, wherever you end up going. Take care. Hope I taught you something. And goodbye.